Picture a neural network in your mind right now. Like, just whatever comes to mind first. What do you see?
I mean, for most people, it's probably something straight out of a sci-fi movie, right?
Yeah, exactly. Like
Yeah.
like cascading lines of green code falling down a black screen. Or maybe you're imagining this incredibly complex flowchart.
Millions of if-then statements just stacked on top of each other.
Right, like a towering skyscraper of Lego bricks. You write a line of code, the computer reads it, and then it makes a decision. It feels very structural.
It feels like reading a really long, incredibly complicated recipe. And, it's entirely natural to visualize it that way.
Because that's what we've been taught, right?
Exactly. That is how we've been taught to think about computing for the last 70 years. We're totally conditioned to believe that machines are fundamentally legible.
Like you could just open it up and read it.
Yeah. You look at line 42 of a program, and you can say, right there, that is where the computer decided to turn left instead of right.
But the deeper you get into modern artificial intelligence and, specifically machine learning, that entire Lego brick recipe reading architecture completely evaporates.
It just doesn't exist.
It doesn't. The landscape of computation becomes something fundamentally different and, honestly, a lot more alien than most of us realize.
It is a profound paradigm shift, really. When you look under the hood of a massive machine learning model, you're not reading a list of instructions anymore.
What are you looking at then?
You're looking at a landscape. You are actually navigating a physical, multi-dimensional space.
And that brings us to what we're doing today. Welcome to the deep dive. The mission today is highly ambitious, but if you stick with us, I promise it will completely and permanently alter how you look at artificial intelligence.
We really want to rip you out of that old mindset of viewing AI as this impenetrable black box of code.
Right. Instead, we're going to reveal the hidden spatial mechanics that are actually driving these systems. We're diving into a wealth of research today specifically. We're grounded in a really comprehensive slide deck titled Geometric ML Engine.pptx.
It's a fascinating breakdown.
It really is. It basically translates all this intimidating linear algebra into literal physical motion.
Which I think is the most crucial translation you can possibly make. Because for you listening, whether you're trying to prep for a technical meeting or you're just insanely curious about how the tools you use every single day actually function.
This geometric perspective is the skeleton key.
It really is. When you stop seeing algorithms as like abstract arithmetic and start seeing them as geometric shapes physically moving, stretching, and folding through space, the math suddenly makes intuitive sense.
It stops being computer science and starts feeling like physics.
Exactly.
So let's jump right into the deep end here. Because to make this leap, we have to completely rebuild our understanding of the most basic building block in this entire field.
The infamous matrix.
Right. The thing everyone fears from high school math.
The grid of numbers.
Yeah. If you stop a seasoned programmer on the street right now and ask them to define a matrix, you'll get a very standard answer.
They'll say it's passive storage.
Exactly. It's a grid. An array. It's basically an Excel spreadsheet with rows and columns, right? You put a number in a little box, and it just sits there waiting to be called upon.
Like a filing cabinet for data.
Yeah, a filing cabinet. But the research totally pushes back on that.
Because that view is entirely sufficient if you're just writing standard software. But in the realm of machine learning, viewing a matrix as a filing cabinet completely blinds you to what's actually happening.
So what's the geometric view then?
The research we're dissecting today shatters that spreadsheet idea. In the geometric view, a matrix is not a passive spreadsheet. It is an active engine.
An active engine.
Yeah, it is a mathematical operator that literally warps the fabric of a vector space.
Okay, I want to make sure I'm really getting this because it's a huge shift in perspective. So let's say a standard programmer sees a matrix as a parked car.
Okay, I like that.
It's just sitting in the driveway holding luggage, which is the data, in the trunk. But geometrically, you're saying the matrix isn't the parked car holding the data.
No, not at all.
It's the engine block itself, actively driving and drifting and accelerating the car through physical space.
That is the perfect way to look at it, actually. The data points, your images, your text, your user preferences, those are the passengers.
Got it.
But the matrix is the transmission. It's the steering wheel, the suspension. When data passes through a layer in an AI model, it is not just being sorted or read.
They're being acted upon.
Violently acted upon.
Yeah.
The matrix grabs the entire coordinate system of reality and fundamentally alters its shape.
That's wild. And the sources actually break down the anatomy of this spatial motion into 4 distinct mechanical actions.
Right. The 4 ways it moves space.
It's fascinating to realize there are really only 4 ways this engine can manipulate the space.
Yeah.
Let's walk through them to make this whole warping concept super concrete.
Let's do it.
So the first one is anisotropic scaling.
Right. And to understand that, we should probably separate the words.
Yeah, because isotropic scaling is a thing too.
Exactly. So isotropic scaling is what you do when you drag the corner of an image on your computer screen to make it bigger.
The whole image grows equally.
Right. The proportions stay exactly the same. It's uniform. Anisotropic scaling, though, which is driven by what mathematicians call a diagonal matrix, stretches the space unevenly.
Give me a physical visual for that. Like, what am I looking at?
Imagine your data is printed on a highly elastic sheet of rubber.
Okay, got it.
Anisotropic scaling means you grab the left and right edges and you pull them outward with all your strength, right? Stretching the image horizontally.
Okay.
But at the exact same time, you gently push the top and bottom edges inward, squishing it vertically.
Oh,
Yeah. And the matrix holds the specific, customized instructions for exactly how much force to apply to every single axis of that space independently.
so we're pulling and squishing reality in different directions at the same time.
Exactly.
Okay, so that's the first motion. The second mechanical action is rotation.
Spinning.
Right. And the research notes this is handled by something called a Givens matrix, using complex roots. Which, I mean, the math sounds like a spell from a fantasy novel,
It sounds intimidating, for sure.
but the core concept is just spinning, right?
Geometrically, it is beautifully simple. You are just spinning the entire universe around a fixed axis.
Like a globe.
Yeah, think of taking a globe and giving it a spin on its tilt. The Givens matrix reaches into the multidimensional space, grabs 2 specific axes, and just turns them like a steering wheel by a very precise angle.
And what about those complex roots, the Euler formulas?
That's just the fundamental mathematical engine that describes perfect circles. It's the math that allows the computer to smoothly, continuously rotate the data without distorting or breaking it.
Okay, so we have stretching, squishing, spinning.
What's next?
The third motion is reflection. Flipping space like a mirror. The sources cite householder equations for this.
Ah, yes, the householder equations.
And reading the formula in the deck, it looks a bit dense. It essentially takes the identity matrix, which is the mathematical equivalent of doing absolutely nothing, right?
Right, the identity matrix is just standing still.
And it subtracts double the outer product of a vector.
Let's translate that entirely out of the math notation because the physical action is mind-bending.
Please do.
Imagine your data space is a massive empty room. Suddenly, you drop a giant, perfectly flat, double-sided mirror right through the dead center of the room.
Okay, big mirror.
A reflection matrix takes every single object on one side of the mirror and instantly teleports it to the exact opposite position on the other side.
Wait, teleporting, so that's subtraction part of the formula.
Is literally calculating the distance. The math looks at where you are currently standing. It calculates your exact distance to the mirror.
So let's say I'm standing 10 feet in front of it.
The formula says, okay, take his current position and subtract 20 feet. It instantly teleports you 10 feet behind the mirror.
Oh, man.
It literally turns the entire room inside out across that plane.
That is a wild way to visualize it. I can actually see the room flipping inside out in my head.
It's pretty cool.
Yeah. All right, the final of the 4 motions is shearing. Slanting space using off-diagonal elements in the matrix.
Have you ever had a thick deck of playing cards sitting perfectly squared up on a table?
Yeah, of course.
And you place your hand flat on the top card and just slide your hand forward?
The whole deck slants.
Exactly. The cards slide over each other. That is a shear.
So you haven't rotated the deck.
Nope.
And you haven't stretched the cards.
You haven't changed their size at all, but you have pushed the top further than the bottom, fundamentally slanting the vertical axis of the space itself.
Let me just pause here and pull all of this together, because what this means for machine learning is pretty staggering.
It really changes everything.
When a massive neural network, say, like image recognition AI, is looking at a picture of a cat, it's not looking at whiskers and ears, is it?
Not at all.
It is taking millions of pixels, turning them into data points, and running them through millions of these matrix engines. The data is being relentlessly stretched, spun, mirrored, and slanted, layer after layer after layer.
Yes. The matrix is a verb. It is an action. Multiplying your data by a matrix means applying physical force to that data.
Applying force.
Yeah, the AI is basically kneading the data like dough until the pattern it is looking for becomes blindingly obvious.
Kneading the dough. I love that. But wait, before we can knead the dough, before we can stretch or spin a space, we need a space to exist in the first place, right?
Yeah, sure.
We need the environment where these data passengers actually live.
You cannot warp reality if you haven't defined reality first.
Exactly. And this leads to a massive concept in the research regarding how we construct what they call the data canvas.
A fundamental architecture.
Right. The material relies heavily on two foundational terms that govern this architecture: basis and span.
Let's unpack basis first.
Yeah, the deck describes it as the linearly independent fundamental building blocks of the space.
Think of the basis as the absolute minimum vocabulary required to describe your environment.
Okay, vocabulary.
Imagine you're navigating a perfectly rigid city grid, like Manhattan.
Yeah.
Your basis vectors might be simply 1 block north and 1 block east.
Just those two instructions.
With just those two instructions, those two fundamental building blocks, you can construct a path to any address in the entire city. You just combine them. Go 5 blocks north and 3 blocks east.
And what does linearly independent mean in that context? Because that's a term that gets thrown around a lot.
It means none of your building blocks are redundant. If your two basis vectors were north and a little bit diagonally north, that would be a terrible vocabulary.
Because you wouldn't be able to go side to side.
Exactly. You would be completely unable to travel east or west. You need fundamentally distinct directions to define a full, usable space.
Which flows right into the concept of span. The span is the entire plane generated by all possible linear combinations of those basis vectors.
Right. So using our city grid analogy, the span is the total geographical area of the city itself.
It's everywhere you can possibly go.
Yes, it is every possible address, every single point you can reach by mixing and matching your north and east building blocks.
Got it.
If you only have north and east, your span is a flat 2D map. But in machine learning, your data might have 10,000 variables.
10,000.
Easily. That means your basis has 10,000 distinct directions, and your span is an unimaginably vast 10,000 dimensional hypervolume.
And here is the absolute revelation for me. This was the massive light bulb moment reading through the source material.
What was it?
Machine learning models manipulate data specifically by changing the basis.
Yes.
They take this massive complex space and essentially rotate our perspective of it until the hidden patterns in the data perfectly align with the axis.
That is the core secret of artificial intelligence. It rarely changes the raw data itself. It changes the perspective from which we observe the data.
That's incredible. And the research outlines exactly how this spatial manipulation translates into the major machine learning tasks that power our modern world.
It breaks it down into 4 main applications, right?
It does. Let's connect this abstract geometry to the tech we use every day, starting with recommender systems.
Ah, Netflix, Spotify.
Right. The mechanism here is matrix factorization, which is defined as D is approximately equal to U times V transpose.
This is the geometry of Amazon and Netflix, yeah. Imagine a gigantic, mostly empty warehouse.
Okay, I'm picturing a warehouse.
We have millions of users along one wall and millions of movies along the other. In the raw data, this is an unfathomably large grid where almost every box is empty.
Because I personally haven't watched 99.9% of the movies in existence.
Exactly. Matrix factorization takes that giant, sparse, empty warehouse and structurally compresses it down into a much smaller, denser set of basis vectors.
So it literally creates a new space.
It creates a space of hidden, latent features. It invents a new geometry where the axes aren't just user A and movie B. The new axes might be amount of explosions, degree of romance, and sci-fi tropes.
Hold on, let me process that. So when Netflix recommends a movie to me, it isn't reading a human-written tag that says action movie.
Not at all.
It's literally performing a geometric translation to see if my personal user data point happens to sit physically close to a specific movie data point on this brand new compressed canvas.
That is precisely what is happening under the hood.
Right.
Through that factorization process, the algorithm has positioned you as a tiny arrow, a vector in this hidden geometric space.
Wow.
And it has positioned every single movie as an arrow in that exact same space.
Wow.
If the mathematical angle between your arrow and the arrow for the matrix is very narrow, it means you are pointing in the same geometric direction.
So I get the recommendation.
Yes, it is pure spatial proximity. It's measuring angles, not reading your mind.
That is wild. Okay, the second major ML task is clustering. The math focus here involves distance matrices and block coordinate descent.
Clustering is what you do when you have a mountain of data and you don't even know what categories exist yet.
You're just throwing it all against the
What,
wall.
you just scatter a million data points into your geometric space. A clustering algorithm uses distance matrices to literally measure the physical spatial gaps between every single point. It is looking for gravitational centers.
And what about the block coordinate descent part?
That is the mechanical algorithm systematically shifting those gravitational centers around the room.
How does it do that?
It tries a spot, measures the distance to all the points, shifts a little to the left, measures again. It does this over and over until eventually the data points fall into neat, tightly packed little solar systems of similarity.
So it organically discovers the neighborhoods of the space.
Exactly.
Okay, the third task is probably the most famous one: classification and regression. This involves solving systems of linear equations to draw boundaries.
If you have a space filled with a cloud of red dots and a cloud of blue dots, classification is the act of trying to slide a literal, perfectly flat sheet of glass right through the middle of the space.
Okay, a sheet of glass separating the dots.
Right. You want all the red dots on the left side of the glass and all the blue dots on the right.
And the math.
Solving those linear equations is simply the math of calculating the exact physical tilt and angle required to wedge that glass between the clouds without hitting any of the dots.
Which sets up the final task perfectly: outlier detection. This focuses on looking for residual errors and rank-deficient projections.
If classification is drawing the sheet of glass, outlier detection is looking for the one dot that is floating miles away from where it should be.
The weirdo dot.
Right. By projecting the data, we can measure the residual error, which is not some abstract statistical concept, by the way.
It's a physical thing.
It is literally the physical distance from the dot to the expected plane. If a point is 50 feet away from the glass when everything else is touching it, it's an outlier. It violates the geometric rules of that space.
Okay, I am fully on board with this geometric visualization. I see the sheet of glass, I see the dots, but I need to inject some reality here.
Sure, go ahead.
When we talk about drawing a perfect sheet of glass between red and blue dots, or solving an equation to find the exact perfect tilt, we are talking about a mathematical utopia.
We are.
In the real world, data is garbage. It's so messy. Sensors fail, humans type the wrong things, data is just missing.
It's chaotic.
The dots don't line up perfectly.
Yeah.
A lot of the time, solving that perfect equation is literally impossible. There is no perfect sheet of glass.
You have just articulated the central crisis of applied machine learning.
A crisis, right.
Pure mathematics demands perfection. It demands a perfect intersection of lines. But the real world completely refuses to provide it. The math shatters when it hits reality.
Which forces the algorithm to make a compromise.
Yes. If we can't have perfection, we need a mathematical framework for the closest possible thing.
And the source material dedicates a massive section to this, calling it the geometry of compromise.
It's all about how to handle unsolvable systems.
Let's visualize the problem first.
Oh,
Imagine our allowed canvas is a flat floor stretching out in every direction.
okay. A big flat floor.
And the answer we are trying to find, the data point we need to hit to solve the equation, is a physical arrow hovering 3 feet above the floor.
It doesn't live on the floor. It lives in a higher dimension.
Right. So no matter how we mix and match our basis vectors on the floor, we can never, ever reach that arrow. The system is unsolvable.
A times x equals b, but b isn't in the column space.
Exactly. But the research introduces a heroic mathematical operator called the pseudo-inverse to handle this. The deck shows it as A plus equals A transpose A inverse A transpose.
The pseudo-inverse is the lifesaver.
It's the mechanism that finds the geometric closest fit. But how does it actually do that physically?
It does it by casting a shadow. Yeah, if you hold a flashlight directly above the tip of that hovering arrow and shine it straight down, it will cast a shadow directly onto the floor.
Okay.
That shadow is the absolute closest physical point on the floor to the tip of the arrow. It is not the arrow itself, but geometrically, you cannot get a millimeter closer without leaving the floor, which you are not allowed to do.
The sources refer to the specific operation for this as the projection matrix. T equals A times the pseudo-inverse.
Right.
It's an operator that forces any wild, impossible vector to cast its shadow exactly onto the plane of viable solutions.
The projection matrix is the flashlight. When an AI encounters a wild, messy, impossible piece of real-world data, it multiplies it by the projection matrix.
And what does that do?
This aggressively squashes the data straight down until it hits the allowed space. It enforces the compromise. The algorithm essentially says, I cannot give you exactly what you asked for, but I will forcefully snap this data to the closest mathematically viable approximation. Without that squashing mechanism, every single AI model would crash the moment it encountered a typo.
But constantly squashing and projecting data has consequences, doesn't it? It changes the nature of the space itself. While we are casting shadows and stretching axes, the overall volume of our space is fluctuating wildly.
It is, yeah. Volume is constantly changing.
And this is where the research brings in a concept that honestly gave me nightmares in school. Determinants.
Oh man, I think everyone hated determinants in school.
Seriously. We were taught to view them as this tedious, arbitrary chore. Cross-multiply these numbers, subtract this chunk, carry the one. It felt totally meaningless.
Just a rote memorization task, but in the geometric view, a determinant has a profound physical identity,
The deck calls them volume scalars.
which is the most accurate name possible.
How so?
Well, imagine your starting basis vectors form a simple, perfect 3D cube. Let's say that cube holds exactly 1 gallon of water.
Okay, 1 gallon cube.
When you apply your matrix engine to the space, stretching it, slanting it, squishing it, that cube is going to be deformed into a slanted, bizarre shape.
A parallel pipette, if we want to get technical.
Exactly. The determinant of that matrix tells you the exact new volume of that shape. If the determinant is 5, your new warped shape now holds exactly 5 gallons of water.
So it's a multiplier.
Yes. The transformation increased the volume of reality by a factor of 5.
And the rules of math say determinants are cumulative. The product rule. Det AB equals det A times det B. If one matrix scales the volume by 2 and the next matrix scales it by 3, the final volume is scaled by 6.
Exactly. But we don't care about determinants just to measure water.
Right.
We care about them because they warn us about the apocalypse.
The apocalypse.
They warn us about the singular state.
Ah, yes. The research has a very ominous warning about this. It states that if the determinant of a matrix is exactly 0, the entire 3D volume collapses completely into a flat 2D plane or even a 1D line.
The spatial dimension is destroyed and cannot be recovered.
This is a catastrophic failure state for an algorithm, isn't it?
Absolutely. If your determinant is 0, it means the volume of your space has been multiplied by 0.
I picture it like an empty cardboard box. It has volume. But a determinant of 0 is the equivalent of a steamroller driving over the box and crushing it perfectly flat into the pavement.
A perfect visual.
The 3D box has been forcefully compressed into a 2D plane.
That is vividly accurate. And the tragedy here is the destruction of information.
How do you?
If I walk up to you on the street and hand you a perfectly flattened, crushed piece of cardboard, and I say, hey, reinflate this back into the exact 3D box it used to be.
I can't do it.
You can't. You have no idea what it looked like. Was it a tall, skinny box, a perfect cube, a short, wide box? You don't know because the vertical axis, the z dimension, was utterly obliterated by the steamroller.
And mathematically, this means the matrix is non-invertible. You cannot hit the undo button.
Which is lethal in machine learning. Training an AI requires running the engine in reverse constantly. It's called backpropagation.
Right, checking its work.
Exactly. The AI makes a guess, checks the error, and runs the math backward to update its weights. If a transformation has collapsed the space and destroyed the dimensions, the reverse gear is broken.
The algorithm hits a dead end.
The math panics, and the training fails completely.
So if dealing with these massive matrices risks total dimensional collapse, and finding these pseudo-inverse shadows requires immense computational power, how do computers actually handle it?
They don't do it all at once, if that's what you're asking.
Yeah, like they don't just swallow these massive million by million grids of numbers whole, do they?
They absolutely do not. A raw, fully populated matrix is computationally exhausting. It is a tangled mess of simultaneous interacting instructions.
So what's the trick?
To process it without completely frying the hardware, algorithms are forced to mathematically dismantle the matrix into safer, simpler components.
Which brings us to a major section of the source material, deconstructing the machine.
Taking the engine apart.
Exactly. There are two primary teardowns or decompositions used to rip these engines apart. LU decomposition and QR decomposition.
Let's look at LU first.
Yeah, the research says LU breaks a matrix, A, into a lower triangular matrix, L, and an upper triangular matrix, U, using Gaussian elimination.
If you recall high school algebra, Gaussian elimination is that incredibly tedious process of adding and subtracting rows of equations to eliminate variables one by one.
Right, until you can easily solve for X, Y, and Z.
LU decomposition is simply taking that exact elimination process and permanently recording the steps into two separate matrices.
Okay, but I need a mental image of a triangular matrix. Why is a triangle helpful?
Imagine your standard square grid of numbers. An upper triangular matrix has data in the top right half of the grid.
Okay, upper right is full of numbers.
But the entire bottom left half below the diagonal line is filled with absolute zeros. It forms a literal geometric triangle of data resting on a bed of nothingness.
And a lower triangular is the exact inverse. The zeros are in the top right.
Yes. And the reason we do this is pure, unadulterated speed.
Because of all the zeros.
Exactly. Solving a massive system of equations when half of the variables have been artificially forced to zero is incredibly fast. The computer doesn't have to juggle complex interactions, it just cascades down the rows, solving one variable, plugging it into the next, and falling like a domino effect.
The documentation explicitly notes LU is the workhorse for solving systems of linear equations and inverting matrices efficiently.
It is the computational bulldozer. It doesn't care about elegance. It just clears out the zeros and gets the job done as fast as the silicon allows.
But then the material presents the alternative, QR decomposition. And this one seems far more delicate.
Very different vibe.
It breaks the matrix A into an orthogonal matrix, which we'll call Q, and an upper triangular matrix R via something called Gram-Schmidt orthogonalization.
If LU is a bulldozer, QR is a precision scalpel. QR cares deeply about the internal geometry of the space. Specifically, it is obsessed with making things perpendicular.
That word orthogonal comes up constantly in the research. It essentially just means perpendicular, right?
Yeah.
Everything at perfect 90-degree angles.
Yes, perfect 90-degree angles. Now, in a multi-dimensional AI space, having a basis where every single axis is perfectly 90 degrees to every other axis is the absolute holy grail.
Why is that so important?
It means there is zero overlap. Moving along the x-axis has absolutely zero effect on the y-axis. They are completely independent.
And Gram-Schmidt orthogonalization is the process that builds that.
Imagine you are trying to set up a massive tent, but all the support poles are crooked, slanted, and leaning on each other.
Sounds unstable.
Very unstable. Gram-Schmidt is a mathematical algorithm that walks up to the tent and systematically straightens the poles, one by one.
Oh, I see.
It takes a sloppy, slanted vector, measures its angle, and forces it to stand perfectly straight at 90 degrees. Then it moves to the next one, forcing it to be 90 degrees to the first.
Just sweeping through the whole tent.
It sweeps through the entire space until it has built a perfect, rigid, orthogonal grid. That grid is your Q matrix.
I see the difference in the mechanism, but I'm looking at the ML applications and I'm a bit confused about the trade-off.
Okay, what's the hang-up? Why doesn't the machine learning model just pick the fastest one, LU, and stick with it forever? Why do we need QR?
Because computers are technically flawed machines. When they do math, they use floating point numbers, which means they constantly round off tiny decimals.
Right, because memory isn't infinite.
Exactly. In a small equation, rounding 0.00001 doesn't matter. But when you are multiplying millions of numbers sequentially in a massive matrix, those tiny rounding errors cascade.
They snowball.
And if your axes are slanted, that error bleeds from one dimension into the next, amplifying until the algorithm's final answer is complete garbage.
It's like trying to build a 100-story skyscraper without using a level. The first floor might only lean by a millimeter, but by the time you reach the roof, the building is literally falling over. That is exactly it. QR decomposition is your laser level. Because it forces every single axis to be perfectly orthogonal, perfectly perpendicular, it acts as a firewall for errors.
Because they're independent.
Right. If a rounding error happens on the x-axis, the 90-degree angle mathematically prevents that error from bleeding into the y-axis. It contains the blast.
That makes perfect sense.
So if an AI is doing something simple, it uses LU for raw speed. But if the data is sensitive or the system is prone to cascading errors, it spends the extra computational money to run QR and ensure the geometric structure doesn't collapse.
Okay, balancing speed with structural integrity. But ripping a matrix into triangles and perpendicular grids is really just preparing the operating table, right?
It's just the setup.
Because the ultimate goal, the absolute holy grail of machine learning geometry, is finding what the research beautifully refers to as the immutable soul of space.
It's a highly poetic title, but mathematically it is entirely accurate. We are talking about eigenvectors.
The pursuit of the natural axis. The documentation states that eigenvectors are the hidden, immutable axes of the transformation. They completely resist rotation, perfectly maintaining their span.
Yes.
Let's ground this. What does an immutable axis actually look like in practice?
Let's go back to our space warping engine. When a matrix grabs reality and stretches, slants, and shears it, almost every single point in that space gets knocked violently off its original trajectory.
A vector that was pointing north might now be pointing northeast.
Exactly. It was swept away by the current of the warp.
The entire room moves.
But hidden deep inside that chaotic, swirling movement, there are a few very special stubborn vectors. When the matrix applies its massive force, these specific vectors simply refuse to be swept away.
They don't move.
They do not rotate. Their fundamental direction remains completely unchanged. They might get stretched much longer or compressed shorter, but they stay exactly, perfectly on their original line. These immovable lines of force are the eigenvectors.
I picture it like a tornado. The wind is ripping everything in circles, pulling houses and cars, but right in the dead center, the axis of the tornado itself is just standing perfectly still, anchoring the chaos.
That's a great physical intuition. They are the natural grain of the matrix. Just like a piece of wood has a grain, every mathematical transformation has a natural grain. And while the eigenvector tells you the direction of that grain, we also have the eigenvalue.
The lambda symbol, the stretch factor.
Right. The eigenvalue is the exact scalar number that tells you how violently the space is being stretched or squished along that specific immovable line.
Knowing these hidden lines leads to what the material calls the power of diagonalization.
Oh, this is the best part.
It really is. It presents an incredibly elegant three-step equation. A equals V times delta times V inverse.
Yes.
You break this down into three simple actions before: unpack, scale, repack.
Yes.
The research literally asks, why does this matter? And the explanation was mind-blowing. Help me translate this for the listener because it's so cool.
It is arguably one of the greatest computational cheat codes ever discovered.
A cheat code.
Yeah. Let's say you are training an AI, and you need to apply a matrix transformation to your data 100 times in a row. Computing matrix A to the power of 100, doing 100 massive, dense matrix multiplications sequentially, is agonizingly slow. It completely chokes the processor.
Because you are constantly recalculating all those messy, slanted, shearing cross interactions over and over. Every variable bumps into every other variable.
Exactly. But diagonalization gives us an escape hatch. Step 1 is unpack using V inverse. The matrix V is literally constructed purely out of our hidden eigenvectors.
Okay, the natural axes.
So applying V inverse shifts our entire frame of reference. It takes us out of the messy standard grid and rotates our perspective until we are perfectly aligned with the hidden natural grain of the matrix.
We've stepped into the hidden dimension.
Step 2 is scale, using the diagonal matrix, delta. This matrix only holds the eigenvalues. And because our perspective is now perfectly aligned with the natural grain, applying the transformation is no longer a complicated, tangled shear or rotation.
It's simplified.
It is reduced to pure, simple anisotropic scaling. We just multiply each independent dimension by its pure scalar eigenvalue.
And step 3 is repack. We use matrix V to shift our perspective back to the normal world, bringing our newly scaled data back with us.
You've got it.
I was trying to come up with an analogy for this. Doing matrix multiplication sequentially, A to the power of 100, is like trying to move a fully assembled furnished house across town by dragging it over the pavement.
It sounds terrible.
It's brutal. Everything shakes, the furniture breaks, it takes forever. Diagonalization is like unpacking the house into individual boxes. You place those boxes on a frictionless, perfectly straight highway where you can accelerate them infinitely fast. And then you just rebuild the house at the destination.
I love that. The highway is the diagonal matrix, delta. Because it is completely diagonal, with zeros everywhere else, raising it to the power of 100 does not require complex matrix multiplication.
You just power the individual numbers.
You literally just take the individual numbers sitting on the diagonal line and raise them to the power of 100. A computer processor can do that in a fraction of a millisecond. You have completely bypassed the nightmare of dense matrix multiplication.
Okay, but this raises a very practical operational question for me. If these eigenvectors are hidden deep inside the math, how does the computer actually find them? They don't glow in the dark.
Yeah, they don't.
The research outlines two distinct methods for hunting them down: the power method and Sure, decomposition.
These represent two totally different philosophies of excavation.
Let's look at the power method first. The mechanism is described as repeated multiplication of the matrix against a random vector feed. The material notes that because the largest eigenvalue dominates exponentially, the vector violently snaps to the dominant eigenvector over time.
Imagine you throw a heavy stick into a swirling whirlpool.
Okay.
At first, the stick bobs around aimlessly. But the whirlpool has a primary dominant current, a strongest line of gravitational pull. Because that force applies itself continuously as the water spins, eventually the stick will stop bobbing and perfectly align itself with that strongest current.
It aligns with the flow.
The power method forces the computer to do this mathematically. You generate a totally random vector and you just multiply it by the matrix over and over and over.
Just grinding it out.
The largest eigenvalue exerts a mathematical gravity. With every single multiplication, its influence grows exponentially compared to the weaker axis. Eventually, your random vector violently snaps into perfect alignment with the primary axis.
The use case listed for this in the deck is the cheap, incredibly fast extraction of just the top one primary axis. And the example given is PageRank, which is the original Google algorithm, right?
Yes, and it's a perfect example. When early Google was trying to rank the entire internet, it didn't have the time or power to map every single nuanced minor relationship between every tiny blog.
That would take forever.
It just needed to find the absolute most dominant, authoritative center of gravity in the web of links. The power method is a brutally fast, cheap way to find the biggest whale in the ocean without having to map the rest of the sea.
But sometimes an AI does need to map the entire sea. And that is where sure decomposition steps in.
Right.
The mechanism here is intense. It uses iterative orthogonal transformations, PUP, transposed to mathematically force the matrix into an upper triangular state, physically exposing the hidden eigenvalues right on the diagonal.
If the power method is throwing a stick into a whirlpool, sure decomposition is a team of meticulous archaeologists excavating a delicate fossil.
Oh, I like that.
It uses a series of incredibly careful rotations, spinning the space without ever warping its volume or angles, to systematically shave away the off-diagonal complexity of the matrix.
Brushing the dirt away.
Exactly. It just keeps brushing the dirt away layer by layer until the matrix is trapped in a triangular shape. And once the dirt is gone, the hidden eigenvalues are just sitting there, completely exposed, lined up perfectly down the main diagonal.
So it is comprehensive, highly stable, but vastly more computationally expensive. It gives you the complete map of the soul of the space.
Yes. And having that complete map is the absolute non-negotiable prerequisite for the final phase of machine learning, because training an AI is not a passive event. It is a grueling mathematical hike across a very dangerous landscape.
This brings us to the final major theme of the research, the topography of loss and untangling variables.
The optimization phase.
Right. If the matrix is the engine and the eigenvectors are the soul, optimization is the terrain we are driving on. And optimizing an AI model, getting it to learn, is essentially trying to navigate a rugged, invisible mountain range in the pitch black, trying to find the absolute lowest valley.
The valley of minimum error, the place where the AI is the least wrong.
Before we step onto that mountain range, the documentation introduces the rules of the terrain with a concept called the matrix bestiary.
I love the term bestiary. It really does feel like classifying wild mathematical creatures.
It classifies 3 specific mathematical beasts that govern how the physical space is allowed to behave. The first beast we've actually already touched on, orthogonal matrices. Q transpose Q equals I.
Right.
The geometric meaning is pure rigid body rotation or reflection. No volume scaling. The determinant is strictly 1 or -1.
This is the rigid spine of the universe. It doesn't stretch, it doesn't squish. If 2 data points are 5 inches apart and you hit them with an orthogonal matrix, they might be relocated to a different part of the room, but they will still be exactly 5 inches apart.
It guarantees safe, non-destructive transportation of data during dimensionality reduction.
Exactly.
The second beast is symmetric matrices. The condition is that the matrix equals its own transpose, A equals A transpose. And the research states this guarantees perfectly perpendicular eigenvectors.
If a matrix is symmetric across its diagonal line, it possesses a magical property. No matter how wild and chaotic the data passing through it gets, its hidden axes, its eigenvectors will always cross each other at perfect 90-degree angles.
There's no slanting of the fundamental framework.
None. This forms the unshakable backbone of things like covariance matrices, which the AI uses to measure how different variables interact with each other safely.
But the third beast is the one that really shapes our mountain range, the positive semi-definite matrix, or PSD.
Yes, the
The
PSD.
geometry here is wild. The rule is the transformation never flips an input vector by more than 90 degrees. What does that actually feel like in practice?
Imagine you are standing in a large field facing directly north. A massive wind, which is the transformation, hits you.
Okay.
If that wind is positive semi-definite, it might push you to face northeast or northwest. It might even push you to face exactly east or west. But it will never, under any circumstances, push you to face south.
It never violently reverses your direction beyond a 90-degree threshold.
It always maintains a general forward momentum.
The application for PSD in the text says it guarantees flawless convex optimization landscapes. And this is where we have to talk about the concept of the Hessian.
The Hessian is the ultimate topographical map of our mountain range.
The material describes the Hessian as the matrix of second derivatives, which dictates the curvature of our error. It compares two completely different physical shapes for this landscape. The first is the convex bowl, which is generated by a PSD Hessian.
Remember, the entire goal of machine learning is to reach the absolute bottom of the lowest valley of error. The Hessian describes the curvature of the ground directly under the algorithm's feet.
So it tells the algorithm which way is down.
Right. If the Hessian is positive semi-definite, meaning all of its eigenvalues are positive, exerting a pure upward stretching force, the landscape forms a perfect, smooth, convex bowl.
I'm picturing a massive, smooth cereal bowl.
Yes. And if you drop a marble into a perfect cereal bowl, what happens?
Gravity effortlessly rolls it down the sides until it rests perfectly at the dead center, the absolute bottom.
Exactly. In machine learning, gravity is an algorithm called gradient descent. On a convex bowl, gradient descent will definitively, safely, and rapidly locate the global minimum. The AI learns perfectly every single time.
But the research doesn't just show the bowl. It shows the nightmare scenario. It shows the saddle point, driven by an indefinite Hessian.
This is the trap that destroys AI models.
Why?
An indefinite Hessian has mixed eigenvalues. Some are positive, stretching the landscape up, but some are negative, pulling the landscape down into a ravine.
The visual in the deck is literally a horse saddle. It curves up in the front and the back, but it drops steeply down on the left and right sides. Why is this so dangerous for the AI?
Because right in the dead center of the saddle, the part where the rider sits the ground is completely flat. The gradient, the slope, drops to zero.
Oh, no.
Now remember, our algorithm is blindfolded. It only knows how to feel the slope of the ground directly under its feet. It walks down the front of the saddle, hits the flat seat, and thinks, the ground is flat. I must have reached the bottom of the valley. I'm done learning.
But it's not the bottom. If it just took one tiny step to the left or right, it would realize it's on the edge of a cliff and would plunge down the side of the saddle toward a much lower minimum.
Exactly. The algorithm stalls. It gets stuck on the ridge, completely deceived by the flat ground, and stops learning prematurely. The optimization completely fails.
So how do we escape the saddle? How do we navigate a 100,000-dimensional landscape full of traps, ridges, and interacting variables?
This is the grand finale.
The final piece of the geometric puzzle is untangling the variables.
This is where every single concept we've discussed today, matrices, bases, shadows, and eigenvectors, unites to solve the ultimate problem of multivariate chaos.
The research presents a before state, interacting variables. It shows a math equation with a cross term, say, variable 1 multiplied by variable 2. The text explicitly states that you cannot optimize variable 1 without simultaneously ruining the optimization of variable 2 because they are chained together by that cross term.
It's a nightmare.
The visual is a chaotic, scribbled ball of tangled lines.
That cross term is the absolute devil of machine learning. It means your variables are physically linked. If you turn the steering wheel to fix variable 1, it automatically slams on the brakes for variable 2.
You're just fighting yourself.
You are trapped in an endless, agonizing loop of overcorrecting because every single step you take in one direction actively breaks your progress in another.
It's like trying to untangle a massive knotted ball of yarn. But every time you pull a string on the left side to loosen a knot, It simultaneously tightens 3 knots on the right side.
It is maddening, and trying to untangle that knot using raw computational force in a space with a million dimensions is mathematically impossible. The universe will end before the computer finishes.
But then, the material reveals the ultimate escape hatch. The solution: change of basis using the eigenvector matrix, V.
Our immutable soul comes to the rescue.
The text explains that by rotating the entire coordinate system to perfectly align with the Hessian's eigenvectors, the cross terms are mathematically eliminated. The visual transforms from a tangled ball of yarn into additively separable tracks, perfectly parallel straight lines.
This is the supreme magic trick of linear algebra. By applying our unpack matrix V inverse, we grab the entire landscape and rotate our perspective until we are looking perfectly down the natural grain of the Hessian.
And what happens to the cross terms?
From this hidden perspective, the cross terms literally cease to exist. The variables are no longer chained together.
Going back to the yarn analogy, it feels like we're trying to untangle this impossible ball of yarn while wearing thick oven mitts. We can't do it. But instead of blindly pulling strings, we execute a change of basis.
We change the rules.
We mathematically change the direction of gravity in the room. And suddenly, under this new gravitational pull, the ball of yarn just magically untangles itself, dropping into perfectly straight, parallel strings hanging from the ceiling.
And because they are straight and parallel, they form 1D optimization tracks. You can now solve each string effortlessly, completely independently in parallel.
Wow.
You turn the steering wheel and the brakes don't move. You just slide cleanly and rapidly right down to the minimum of each track. The tangled, impossible nightmare is instantly transformed into a perfectly organized, frictionless highway.
It is incredibly satisfying to see how all of these abstract, intimidating mathematical formulas exist purely to solve tangible spatial problems.
It really grounds the math.
It brings us to the summary of our deep dive today. The research closes with an elegant visualization titled The Architecture of an ML Model, linking everything to 4 sequential pillars.
Where?
Let's trace the full journey of the data. First, we have the canvas.
The data. Raw information is not just a list of numbers. It is instantly transformed into a geometric vector space, bound strictly by the rules of its basis and its span. That is the room we operate in.
Second, the transform, the operations. The weights inside the neural network act as active physical engines. They violently rotate, scale, shear, and squash the data, casting shadows and warping the volume of the space.
Third, the structure. Eigendecomposition. To prevent the math from collapsing into chaos, the algorithms actively hunt for the natural, unmoving axes. They use these hidden lines to pry apart interacting variables and expose the clean, independent factors underneath.
And finally, the engine, optimization. All of this intense mathematical geometry exists for one singular purpose: to shape a smooth topography. It molds the landscape so that gravity isn't trapped on a flat saddle, but can securely and inevitably pull the data down to the bottom of a perfect convex bowl.
So for you listening to this, the next time you read an article about a new AI learning from a massive data set, I want you to banish the image of a glowing mechanical brain or endless streams of green code.
Picture the architecture. Picture massive, multidimensional geometric spaces violently snapping into alignment. Picture the fabric of reality, stretching along invisible axes, projecting shadows to force compromises, and untangling impossible knots so that data can slide effortlessly down a perfect mathematical slope.
It is a violent, beautiful, spatial ballet.
It truly is a completely different way to look at computation.
It really is.
And as we wrap up, I want to leave you with one final, slightly provocative thought that occurred to me while digesting all this geometry.
Ooh, I'm intrigued.
We have spent an hour talking about how silicon machines use eigendecomposition to untangle chaos and understand data. But think about your own biological brain for a moment.
Okay.
Think about what happens when you are wrestling with a massively complex, tangled problem in your life. You are confused, everything is interacting, you're stuck on a saddle point, and then suddenly you have an aha moment.
An epiphany.
Right. Things click. You literally say the phrase, "I just needed to look at it from a different perspective."
I see exactly where you were going with this.
Right. If the absolute cutting edge of artificial intelligence fundamentally boils down to discovering the hidden geometric axes of data to untangle a mess, it raises a profound question about human intuition.
It really does.
When we have a sudden realization, when the noise clears and we finally see the core truth of a situation, are our biological brains actually performing a massive instantaneous eigendecomposition on the chaos of the world around us? In those rare moments of absolute clarity, are we simply discovering the eigenvectors of our own reality?
That is a staggering parallel to consider. We are mathematically changing the basis of our own understanding.
Something to ponder the next time you have a brilliant idea. Thank you so much for joining us on this deep dive into the geometric engine of machine learning. Keep questioning the hidden shapes and structures of the world around you, and we'll see you next time.